Hello, in this short video we are going to discuss turbulence models available in CONVERGE. Turbulence is a state of chaotic and unstable fluid flow, characterized by large Reynolds numbers and high rates of mixing and heat transfer. The enhanced mixing is the result of turbulent eddies in the flow. These turbulent eddies occur at many length scales, even those too small for the discretized domain to resolve. To resolve the eddies occurring at the smallest length scales, you either need to refine the grid or use a turbulence model. The former solution is not practical for many applications due to its computational cost. This is where turbulence modeling comes in. Modeling turbulence allows you to account for the enhanced mixing effects of turbulence at a significantly reduced cost compared to directly resolving all the turbulent length scales. CONVERGE offers three approaches for modeling turbulence: the Reynolds Average Navier-Stokes, or RANS, the Large Eddy Simulation, or LES, and a RANS-LES hybrid. CONVERGE includes several models for each of these approaches, which we'll now discuss in more detail. For RANS models, the flow variables such as velocity are decomposed into an ensemble mean and fluctuating term. When this decomposition is substituted into the Navier-Stokes equation, an additional term called the Reynolds stress term, which represents the effects of turbulence, is produced. The different RANS models use different methods to model the Reynolds stress tensor. It is important to note that the smallest length scale resolved by RANS is given by the following expression. If your grid size is not small enough to resolve the scales given by the expression, the simulation will be under-resolved. Additionally, for RANS, you will not be able to resolve any smaller length scales, even if the grid is further refined. There are many RANS models available in CONVERGE, including standard K epsilon, standard K omega, and Spalart-Almaraz. Take a second to look at the full list shown here. When selecting the correct RANS model for your simulation, you should consider factors such as the application, the type of flow you expect, and the geometry you're working with. For example, if you're working on a case with a low Reynolds number wall-bounded flows, you may be deciding between the V2F model and the standard K omega model. While the V2F model exhibits superior behavior with highly resolved walls, it is more costly. The standard K omega model is good at predicting transitions and is less costly, but it is sensitive to free stream conditions. The table on the screen summarizes the advantages and disadvantages for each RANS model. Moving on, the LES approach directly resolves large-scale turbulent motion and models the small-scale eddies. In this approach, the grid cells act as a spatial filter which decomposes the velocity into a resolved field and a subgrid field. Inserting the decomposed velocity into the Navier-Stokes equation yields the LES equations, which contain an additional term called the subgrid scale tensor. The various LES models use different methods to estimate the subgrid tensor. Because the grid acts like a filter, unlike RANS models, an LES simulation can resolve the smallest turbulent length scales by simply refining the grid. However, refining to this level may be too computationally expensive. LES models are broken up into three categories: zero equation models, one equation models, and two equation models. The list here shows all the different models in each category. The categories are named based on the additional number of transport equations the model must solve. For zero equation models, CONVERGE does not solve any additional transport equations. For one equation models, CONVERGE solves an additional transport equation for the subgrid kinetic energy. And lastly, for two equation models, CONVERGE solves additional transport equations for subgrid kinetic energy and subgrid dissipation. Like the RANS family of models, the particular LES model you'll want to choose depends on a variety of factors. You can pause and review the table on the screen, which summarizes the advantages and disadvantages of each model. When deciding whether to use a RANS or an LES model, you should consider the trade-off between accuracy and computational expense. RANS is computationally less expensive compared to LES, but may lack accuracy in predicting turbulent flow details. LES, being more computationally intensive, provides better accuracy in resolving turbulent flow structures. CONVERGE also provides hybrid models that combine both RANS and LES approaches in order to gain the advantages of both and mitigate their disadvantages. The hybrid models we offer include the Delayed Detached Eddy Simulation Model, or DDES, the Improved Delayed Detached Eddy Simulation Model, or IDDES, and the Stress Blended Eddy Simulation Model, or SBES. Now, let's go over how to enable turbulence modeling and select a model in CONVERGE Studio. First, click Physical Models in the Case Setup dock. Then you'll want to click the check mark next to the turbulence modeling, and here it's already checked, and hit Apply. If it's not already checked, you'll see it appear underneath the physical models. Next, click Turbulence Modeling to open the Turbulence Modeling panel. First, you must decide the method of turbulence modeling you want to use, RANS, LES, or hybrid. We'll choose RANS for this example. Now, click on the model field to see the drop-down list of models to choose from. We'll just keep with standard K omega. Next, you're free to tune the parameters for your chosen model or use the recommended values provided by CONVERGE. You can always return to the recommended values by clicking the Set Recommended Values button down here. Only the tabs applicable for your model are available. The others will be grayed out. Since we have chosen RANS, here the DES, LES, and SBES tabs are unavailable. In addition to the parameters for your model, there are a couple other settings worth mentioning. On the Wall Modeling tab, you can configure global settings for the near wall treatment and the wall heat transfer model. On the Pratt-Schmidt number/viscosity tab, you can configure the physical constants and other settings that are used in all turbulence models. And on the Physics Effects panel, you can configure how turbulence modeling interacts with the physical models in simulation, such as Lagrangian partial modeling and buoyancy. Lastly, click Validate to ensure there are no errors or warnings, and then click OK to close the panel. If there are no issues, you'll see a green check mark next to turbulence modeling in the Case Setup dock. And that brings us to the end of this video. For more details on CONVERGE's turbulence models, please refer to our in-depth training materials and user manuals on the Convergent Science Hub. Thank you for watching.